All right, now we're going to take a look at a way to think about the derivative, really an applied way to think about the derivative. And it really gets down to how we define the derivative at first. Our motivating question for finding the derivative was to be able to find the slope of a tangent line. And if you think about a line, like an actual line, the slope describes how it changes, right? Does it change quickly? You know, is it a steep slope or is it, a shallow slope? And is it increasing or decreasing, right? Is the slope positive or negative? It describes how the function, how that line changes. Now, with any curve, right, the derivative does that for us. The slope of a tangent line, it just tells us how it's changing at that instant. So the derivative for any function will tell us the instantaneous rate of change, right? How the function is changing at one particular instant. Without the derivative, the best we can do is find an average rate of change, right? See how much the outputs change over some change in the x coordinates, in the x values, in the input values. It's with calculus that we're able to pinpoint how to describe how a function is changing right at that one moment, right? That's what the limit does for us. And that's how we set up that limit definition for the derivative. So since the derivative is a rate of change, we can now maybe see how derivatives can be used in a lot of applications, right? So if I have a function, right, so I'm kind of, this is sort of written out here a little bit in the preamble to this section, but if I have a function that tells me displacement over time, right? So if s of t gives displacement at time t, right? So I've got displacement as a function of time. Then the derivative of that will tell me the rate of change of displacement over time. And the rate of change of displacement is velocity. And so this is sort of one of our very first types of applied examples, is that velocity is a derivative of displacement. That's going to play a role. We're going to see that several times. There's going to be a whole section in the next chapter about it, and then another whole section where we work with it in chapter 6, that concept. But this is just one example of the derivative being used in an applied setting, right, to kind of help us understand the relationship between a couple of quantities. So, and in general, the derivative is just a rate of change with respect to change in some input variable. So in example 216, they tell us that the displacement in feet of a free-falling object is given by s equals 16t squared, where we measure time in seconds there. So I could use that function and say, well, after, if I knew how many seconds have fallen, how many seconds have elapsed, I can determine how far the object has fallen. We want to find the instantaneous velocity of the object at t equals 4 seconds. So what that means is we want the instantaneous velocity, that's the derivative of displacement over time. And then we're going to evaluate it when t is equal to 4. So our function, I'll call it s of t, is 16t squared. So we know how to find the derivative, right? We're going to find s of t plus h. That is 16 times t plus h squared. And then we can do some algebra here. 16, and let's see, we'll FOIL out the t plus h, we get t squared plus 2th plus h squared. And we can distribute the 16. Okay, so this is s of t plus h. Now let's subtract s of t. If we're subtracting this function, that means we're subtracting 16t squared. And we got 32th plus 16h squared. And having found the expression for that difference, we can set up our derivative limit. So ds dt is the limit as h approaches 0 of s of t plus h minus s of t all over h. So up top we've got 32th minus 16h squared all over h. This is like one of the earlier functions we worked with, right? It's just a polynomial, so the algebra is fairly straightforward. We could see that we could factor out an h. So we have 32t minus 16h all over h. We know what's coming now, right? We're going to cancel these h's. So we want the limit as h approaches 0 of 32t minus 16h. And as h approaches 0, then 16h approaches 0, and we are left with 32t. So this is ds dt, right? And ds dt is the velocity function, right? These are one and the same. We want to evaluate this when t is equal to 4. So let's do that. And then as we do that, we'll actually see why I really like that ds dt notation rather than s prime notation, especially for applications. So at t equals 4 seconds, right, v of 4, whoops, which is the same as ds dt evaluated at t equals 4, is 32 times 4, and this is, that gives us 128. Now, this is an applied problem. We should have units, right? On the one hand, we could see, all right, well, it's a velocity function, and what types of units do velocity have? And then just going back up here and reminding ourselves what our sort of linear and time units are, we could see, oh, well, it'll be feet per second, right? And that's true, right? So we do get 128 feet per second. And in a scenario where we have a really, common rate like velocity, so we know what types of units those should be, it's not so bad. But sometimes we're doing a problem and it might be hard to remember, oh, well, what unit should we end up with when we take the derivative? So ds dt, with this notation, there's no guesswork about what our units should be. If it's ds dt, then we have units of s over units of t. So like the dy dx or ds dt notation carries with it an interpretation of like what those units ought to be. So a lot of the time you'll see me just default to using that notation. I find it helpful. All right, let's try another one. Here we've got a spherical balloon being inflated. So just imagine that it's a perfect sphere, right? Find the expression for the instantaneous rate of change of volume. Instantaneous rate of change of the volume, and then with respect to the radius. So that part at the end, right, with respect to, that's a really important part of the derivative. We know that if we want an instantaneous rate of change, we are looking at a derivative, right? Always. An instantaneous rate of change is a derivative. But it's important to know what variable we're respecting, right? When we find the slope of a tangent line, we want dy dx. That's with respect to x. When we find the velocity, right, that's a time rate of change here, right? That's feet per second, right? This is a change. We're taking the derivative with respect to time. Here, we're going to find the instantaneous rate of volume with respect to the radius. And so that means that the first thing we want to have is a function of volume where the independent variable is the radius. And we have that. But before I write that down, I'm just going to kind of make a note based on what I've highlighted here. I like to do this when I'm starting out a problem, just, I know what they've asked us to find in English, so I want to just sort of write it in calculus. We want dv dr, the instantaneous rate of change of volume with respect to radius. So now if I want dv dr, then what I really want is a function of volume written with the variable radius. And we have that. You could look it up, and it's probably in the inside cover of some books, or in posted about a million different places. If you just search Google volume of a sphere, you'll be reminded that the volume of a sphere is given by 4/3 pi r cubed. And just so you know, this isn't a formula I would expect you to memorize. I've used it so much that I just know it. But if you were working on a problem, on a quiz or a test, or you needed to use a problem like this, I would include a little note like, and just so you know, remember that the volume of a sphere is given by 4/3 pi r cubed. So this is our equation that we're going to start with, and that's our function. That is our f of r. And now we could do the algebra we need to do to set up our limit. So this is f of r. So f of r plus h is 4/3 pi r plus h cubed. And like we often do, I'm going to cube out, I'm going to expand that r plus h cubed. You can use Pascal's triangle to help you. And you will get r cubed plus 3r squared h plus 3r h squared plus h cubed. Now, a lot of the time, once I get to this point, I say, okay, let's go ahead and distribute that factor. In this case, it would be 4/3 pi. I'm not actually going to leave that factored out just because I'm a little, I think it'll be less writing overall to leave that factored out in this case. And we'll be able to see everything cancel that needs to cancel in just a moment. So there's our f of r plus h. Now, f of r plus h minus f of r is, okay, so here's f of r plus h. And then minus f of r, minus 4/3 pi r cubed. So rather than distribute the 4/3 pi to everything in the first product there, I'm going to just say, oh look, I actually have a common factor of 4/3 pi, and I'm going to factor that out. So inside now I've got r cubed plus 3r squared h plus 3r h squared plus h cubed minus r cubed. The r cubed and the minus r cubed cancel. Everything that's left here has a factor of h, right? There's the h, there's an h, there's an h. So I'm going to factor out an h. 4/3 pi h times 3r squared plus 3rh plus h squared. All right, this is what's going to go in the numerator of that limit. So dv dr is the limit as h approaches 0 of f of r plus h minus f of r all over h. This is the limit as h approaches 0 of, all right, so this is what's in the top. That's what we found. In the bottom, you've got just a factor of h. We know what's coming now, right? We're going to cancel those h's. So we want the limit as h approaches 0 of 4/3 pi times 3r squared plus 3rh plus h squared. Now it's no longer a problem to let h be 0. If h is 0, that does not cause us to divide by 0. So letting h equal 0 means that this will go to 0, right? Any term with a factor of h will go to 0. That goes to 0 and that goes to 0. Whoops. So we've got the limit as h approaches 0. Oh, whoops. I'm getting a little kind of got excited and forgot. We're letting h approach 0. We don't have to write lim anymore. 4/3 pi times 3r squared. Let's simplify. We can cancel those 3's. We get 4 pi r squared. Look, this is the function that describes how the volume changes with respect to radius. It tells us for some kind of small change in the radius, what kind of change in volume does that produce? So this is the first thing it asked us for. It wanted the instantaneous rate of change of volume with respect to radius. Here's the function that describes that. Now if we go back up here, it says then evaluate this expression when the radius is 2 meters. So we still need to do that. So dV dr when r is equal to 2 meters is equal to 4 pi times 2 squared. So 2 is 4, 16 pi. 16 pi. Okay. Now what should the units be? Think about this for a minute. Maybe pause the video if you want to think about it before I ruin the surprise. Maybe it won't be a surprise. I probably shouldn't say it that way, but so I'm using this dV/dr notation. I'm writing it as dV/dr instead of v prime for a reason. And that reason is that I know I just need units of volume, and volume would be in meters cubed over units of radius. Radius is just meters. So this would be cubic meters per meter. Now you could approximate 16 pi if you want. If you throw that in the calculator, you'll get 50.27 cubic meters per meter. Right? Either of these is fine. Now, you might be thinking, cubic meters per meter, why don't I just call that square meters, right? Cubic meters, meters cubed over meters is equal to meters squared. I mean, that is how those units interact there. I write it as meters cubed per meter because we are finding a rate of change, and meters cubed per meter gives some context. We're talking about an effect of how the volume changes with a change in the radius compared to a change in the radius. And when you express it as a rate, that implies that comparison. So it's more meaningful to write this answer as meters cubed per meter than meters squared. Also, here's a super interesting fact here. Get ready. You might not be aware because it's not a formula that comes up all the time, but you know, the volume, we know that the volume, right, of a sphere is 4/3 pi r cubed. But the surface area of a sphere is 4 pi r squared. So a couple of interesting notes, right? I mean, when we took the derivative, we end up with something that has units of meters cubed per meter, which you could think of as meters squared if you want. And that expression, right, is the same as dV/dr. So like, it's almost something weird. It's like the sphere knows its own dV/dr, right? Like there's some inherent like relationship between the surface area of a sphere and the rate at which the volume changes with respect to radius. So I'm going to give you a second just to kind of absorb that and appreciate how cool it is. All right, we got one more example in this section. And I'm going to preface this example by saying I don't have a background in circuits, right? And that's okay. Like, I don't necessarily need to have a background in the actual application in order to do the problem, in order to read and understand what they're telling me. Certainly, I think if you have a background or if you're learning about circuits, that can make this a richer example and give you some context that can be helpful. But if you don't have that background, that's okay, is what I'm saying. I don't think you won't be at a disadvantage from a calculus perspective. So we're just going to learn how to read this. And in a pre-calc or algebra course you've taken, you probably did some direct variation or proportional, proportionality like relationships. So this is one of those types of problems. And they're giving us a bunch of information. So the first thing they say, I'm going to kind of try to separate it out, is that the power P produced by an electric current I in a resistor varies directly as the square of the current. I'm not going to read any further right now, and I'm just going to take this highlighted, this yellow highlighted sentence, and I'm going to write it mathematically. If P varies directly as the square of I, that means that P is equal to some constant K times I squared. And by the way, if you're used to little I being like the square root of -1, like the complex number, the imaginary number, it's true that in a lot of mathematics books, most math books, they'll use I for that. But in engineering math books, they use J for that. And the reason is because little I is used as a variable current. And so in an engineering mathematics book, they adopt notation that is used in a lot of engineering fields. So here a power is this function of current, right? So if I know the current, I could find the power. Sort of, right? Almost. I just don't know what K is yet. So K is just some constant. Now let's keep reading this problem. Given that 1.2 watts of power are produced by a current of 0.5 amps in a certain resistor. I'm going to stop. I'm not even going to finish reading that sentence. Because that piece of information here tells me that P is equal to 0.5 when, oh no, sorry, P is equal to 1.2, right? So watts, that's power. 1.2 when I is equal to 0.5. And we can use this to find K. Right, so that'll give us the specific function of P in terms of I. So let's, and this is algebra, right? So none of this is calculus yet. We get 1.2 is equal to K times 0.5 squared. 1.2 is equal to 0.5 squared is 0.25, so we have 0.25K. And then you can just divide both sides by 0.25. And 0.25 is 1/4, so when you divide by 1/4, that's the same as multiplying by 4. And so on the left side we get 4.8 is equal to K. And that means now that our function for this problem is P equals 4.8 I squared. All right, so now all of that in the beginning, right? All of this was a preamble in this problem to just give us the function that we needed. Now let's keep going. This says, find an expression for the instantaneous rate of change of power with respect to current, and then we'll evaluate it when I is 2.5A. So what we want, 2.5 amps rather, we want rate of change of power, dP, with respect to current, di. We want dP di, and we have power as a function of I, so that's perfect. So let's find, this P function, this is like our f of I. So f of I plus h is 4.8 times I plus h squared. So let's see, that's 4.8 times I squared plus 2IH plus h squared. And I'm going to leave the 4.8 factored out this time. You could distribute it. It'll work out just fine either way. We want dP di, which is the limit as h approaches 0 of f of I plus h minus f of I all over h. So this is the limit as h approaches 0 of, let's see up top, there's our f of I plus h minus f of I, 4.8 I squared. I'm going to factor out the 4.8 up there. I squared plus 2 IH plus H squared minus I squared, and up in the numerator, right, we could cancel these, the plus I squared and the minus I squared. And now everything left up there has a factor of H. Let's take that out. So taking out the H, we've got 4.8 H times 2I plus H. And now that we've taken out the factor of H, we can cancel it with the 1 in the bottom. We like where this is headed. We're getting really close to just letting H approach 0, because now we're allowed to let H approach 0. We're no longer in danger of dividing by H. So this H goes to 0. So we have 4.8 times 2I, and that is 9.6I. This is dp di as a function. Right, so here's the function that describes how power is changing with respect to current. The last thing this problem asked us to do was to evaluate this expression for I equals 2.5 amps. So let's do that. (9.6 times 2.5), that gives us 24. And what should the units be? If you want to give this some thought, maybe pause the video before I write it out or talk about what the units ought to be. So going back to this notation, the dpdi, I know that my units are going to be units of power, which will be watts, over units of current, which is amps. So this is watts per amp.